Oil rigs weighing hundreds of thousands of tons sit motionless in the open ocean. Here is the engineering that makes that possible. There is not a single anchoring method. The solution changes entirely based on water depth. From steel legs punched into the seabed to chains shaped by a single mathematical curve, to floating vessels held in place by nothing but algorithms and thrusters. The deeper you go, the more radically the engineering transforms. Jackup rigs represent the starting point for offshore anchoring, operating in water depths up to about 400 feet. These rigs arrive at site as floating hulls towed by tugboats, with their steel legs retracted above the deck. Once positioned, each leg is lowered to the seabed using a rack and pinion jacking system, a mechanical arrangement where the pinion gear, powered by hydraulic or electric motors, climbs a fixed rack of steel teeth welded along the leg. As the gear turns, the leg is driven downward until it contacts the sea floor. Only then does the hull begin to rise, lifted clear of the waves as the legs transfer the massive weight of the rig directly into the seabed. The entire self-elevating process relies on precise synchronization. Centralized hydraulic synchronizers keep all legs moving in unison, preventing uneven loading that could twist the hull or overload a single leg. Once the desired elevation is reached, heavy-duty mechanical locks engage, bracing the structure against wind and wave forces. Sensors monitor the position and torque on each leg, automatically shutting down the system if any anomaly is detected. The practical limit for jackup rigs is set by the strength and length of their legs. Beyond about 400 feet, the legs would need to be so long and robust that they would buckle under their own weight or become impossible to transport. Soil conditions also matter because soft or uneven seabeds can reduce bearing capacity, increasing the risk of settlement or tilt. For these reasons, jackup rigs dominate only the shallowest offshore fields, where their direct load path and rapid deployment make them the most efficient solution. As water depth increases, the limitations of jackup legs force engineers to seek entirely different anchoring strategies. Beyond the reach of jackup legs, engineers turn to fixed jackets and compliant towers, structures that anchor platforms in water depths from 300 to 2,000 feet. A fixed jacket is a steel lattice frame assembled on shore and transported in massive sections. At the site, the jacket is lowered onto the seabed, then secured by driving steel piles deep into the ocean floor. Each pile acts as a giant nail, transferring the platform's weight and resisting the lateral push of waves and wind. The jacket's geometry, triangular bracing, and wide base delivers stiffness, allowing it to behave as a rigid cantilever. This rigidity, however, comes at a cost. As water depth increases, the jacket must grow taller and heavier, pushing fabrication and transport to their limits. Heavy lift vessels can only handle jacket sections up to about 150 meters long, and beyond that, the logistics and cost curve rise sharply. To extend reach without the penalty of sheer mass, compliant towers introduce flexibility by design. These slender towers are engineered to sway with the ocean, not against it. Their natural period is tuned to avoid resonance with dominant wave frequencies, reducing peak loads on the piles and on the structure. Troll A, standing 472 meters tall off Norway, embodies this principle. As one of its engineers put it, Troll A was designed to sway like a giant seaweed, letting the ocean's energy flow through the structure rather than fighting it. This engineered flexibility allows compliant towers to survive in depths where rigid jackets become uneconomical or impossible to build. But even the most advanced tower eventually hits a limit. When steel and concrete can no longer be transported, assembled, or made strong enough, the industry must turn to floating solutions. Semi-submersible platforms mark the first leap from fixed to floating anchoring. In water depths from 1,500 to 5,000 feet, the ocean floor lies too deep for any rigid tower or pile. Instead, these platforms float stabilized by a network of mooring lines that stretch from the hull down to anchors on the seabed. The key to their stability is not just the anchor, it is the geometry of the mooring itself. Each line hangs in a broad curve known as a catenary, shaped by the balance of its own weight and the tension at each end. The mathematical form of this curve is y equals a times the hyperbolic cosine of x over a. Heavier chains provide more restoring force, but their weight becomes a burden in deeper water, so engineers transition to lighter steel wire rope and eventually synthetic fiber as depth increases. This progression, chain near the surface, wire rope in the middle, polyester or HMPE at the greatest depths, lets the mooring remain strong without overwhelming the platform with excess weight. The entire system acts as a mechanical shock absorber, with the catenaries sag-absorbing wave and wind loads, restoring the platform to its set point without rigid restraint. As depth grows, the anchors themselves must change as well, paving the way for suction piles and other advanced anchoring methods. Suction caissons operate on a principle both simple and powerful: turn a steel cylinder into a vacuum anchor by pumping water out from inside. Each caisson resembles an enormous upside-down bucket, typically 6.5 meters across with a projected area of 33.2 square meters. When set on the seabed, remotely operated vehicles initiate the pump-out sequence. As water is evacuated, a pressure differential forms, drawing the caisson downward as if pulled by an invisible hand. The resulting vacuum at 101 kilopascals multiplies across the caisson's footprint, generating a holding force calculated at 3.36 meganewtons for a single unit of this size. This number is not theoretical. On the Diana platform in the Gulf of Mexico, 4 such caissons were installed at a depth of 1,500 meters. The remotely operated vehicle pilot Maria Pascual described the operation. She said, "Lowering a 30-meter suction caisson to 1,500 meters is like placing a needle in a moving ocean. We rely on the remotely operated vehicle's eyes and the pump-out rhythm to keep it steady." The system's genius lies in its reversibility. To remove the anchor, engineers simply repressurize the caisson, break the seal, and allow it to be extracted intact. This approach not only delivers immense holding power, but also enables recovery and reuse, a rare advantage in deepwater anchoring. Suction caissons form the foundation for the even more complex tendon and mooring systems required as platforms push into greater depths. Tension leg platforms, or TLPs, changed deepwater engineering by using vertical steel tendons held under constant pretension. Each tendon, anchored with piles, is kept tight by making the platform slightly more buoyant than its weight. This balance creates an upward force, stretching each tendon with 30 to 54 meganewtons. The buoyancy to weight ratio hovers just above 1, and tendons remain nearly vertical, deviating less than 5 degrees even at depths over 2,000 meters. The result is a platform that barely moves vertically, with heave limited to a few centimeters, allowing wellheads to stay safely on deck. Spar Platforms took another path. The Perdido spar in the Gulf of Mexico, set at 2,438 meters, uses a deep draft cylinder extending more than 200 meters below the surface. Stability comes from a low center of gravity, with dense ballast at the base and buoyancy above. This creates a metacentric height of about 55 meters and a restoring moment near 5 meganewton meters per degree. Perdido's hull alone cost nearly $3 billion, but the design lets the platform ride out long waves with minimal motion, making ultra-deepwater production possible where anchors fail. TLPs rely on vertical tension for stability. Spars like Perdido use mass and geometry. Both mark the final stage of passive anchoring before dynamic positioning takes over. Dynamic positioning replaces every physical anchor with a constant stream of calculations and corrective thrust. On a modern drill ship, dozens of sensors feed data to the control system. Triple redundant GPS antennas track position to within 5 centimeters, while seabed acoustic transponders and gyros provide backup if satellite signals fail. The heart of the system is a closed-loop controller that solves for the vessel's position, heading, and velocity up to 10 times per second. Each cycle, the computer issues new commands to a ring of azimuth thrusters rotating propellers mounted around the hull, each capable of delivering several megawatts of force in any direction. The system automatically balances the thrust to counteract wind, wave, and current, keeping the vessel on station without any contact with the seabed. Redundancy is built into every layer. If a GPS receiver drops out, the system averages the remaining signals and cross-checks with acoustic beacons. If a thruster fails, the control algorithm instantly redistributes power among the remaining units to maintain position. This architecture allows dynamic positioning vessels to operate in water depths where mooring would be prohibitively expensive or slow to deploy. In the event of a hurricane or emergency, the ship can disengage station keeping and leave the site within minutes, an agility that fixed anchors cannot match. A dynamic positioning engineer once described the system this way: "We don't anchor to the seabed, we anchor to math and microseconds. The ocean never stops pushing, so neither do we." With dynamic positioning, the ocean's depth becomes almost irrelevant. The ship's place is held not by steel or concrete, but by a continuous dialogue between sensors, algorithms, and electric thrusters, an invisible tether recalculated every second. Every advance in offshore anchoring pushes the limits of engineering as the search for energy moves deeper and farther from shore. These systems are not just technical marvels, they determine the safety, feasibility, and environmental impact of global energy. Precision at depth remains an ongoing engineering imperative.